Hello there. Welcome back to Chemistry for Engineers. And this is our chapter 4. Okay. And stoichiometry. And what I want you to do real quick is you're going to need to get your notes template to fill in. You're going to need to get your periodic table. Okay. So go get your notes. Oh, you should have your notes template because you're watching this and you have to fill it in for class. Okay. And you need your periodic table and your ion list. And you are going to need a calculator for today. And there is a lot of math in this chapter. So I want you to be ready to pause so that you can work at typing it into your calculator at the same time. If we were doing this in class, I would be I would be setting things up and then being like, okay, you guys calculate it. And you want to make sure that you're typing these into your calculator correctly, that you know when to multiply, when to divide, so that when it comes time to do your homework and the test, you're ready. I always say that chemistry is a study in action, not in passive learning. I say it's not an audiobook. So you need to be actually doing things in order to really understand stoichiometry. So be ready to pause this video and to type things into your own calculator and to make sure that you're getting the same answers that I am getting. All right, let us begin. Okay, so first of all, let's take a look at a couple things here. And sorry, I'm setting things up over here a little bit differently. All right, so I'm going to try to let you know a little bit more about what slide we're on, because that sometimes helps. So this is slide 2. And we're looking at gasoline and other compounds that are primarily or predominantly hydrocarbons. So most of the hydrocarbon molecules in gasoline are something called an alkane. Okay. Alkanes are compounds whose carbon atoms are linked together by single bonds. Okay. So alkanes have a general formula of CnH2n plus 2, where n is an integer. So what that means is that if you have C3, then you would have 2 times 3, which is 6, plus 2 is 8, H8. So that's what that means. So whatever this is, this would be 2 times 3 plus 2. Okay. Now, hydrocarbons specifically are molecules that contain only carbon and hydrogen atoms. They don't have anything else, no oxygen, no nitrogen, nothing else, just hydrocarbons. Okay. All right. So here are some examples of alkanes, and we are on slide 3 now. Okay, now let's take a look at how these would be drawn in a different way. So here we have methane and CH4, and this is a ball and stick model, but if we weren't doing a ball and stick model, we would draw a Lewis structure that looks like this. Okay, and then our next one would be ethane, C2H6, and it would look, and I'm going to kind of toggle back and forth so that we have some additional space. So our ethane or C2H6 would look like this. We put 2 carbons, and then the hydrogens go like this. And this is the way all alkanes, simple alkanes, are going to work. Okay. And then we can have our propane, C3H8, and that'll be 3 carbons together like this. And here we'll have hydrogens on each one. Like that. Okay, now let's come down here to butane, C4H10, and that one will have 4 carbons. Accidentally made an extra line there. There we go. See, we have 4 carbons, and then we set this up, and this is how you draw these alkanes. All right. And I'm going to be showing you pentane on the next slide. So alkanes, simple alkanes are really simple. You just draw that many carbons and surround them by your hydrogens. Okay, so now let's take a look at isomers. Isomers exist. First of all, this is slide 4. Okay, isomers exist when two or more structures have the same chemical formula, but a different shape. So let's take a look here at our pentane. And we have CH3, CH2, 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 CH3. So that's describing kind of what this looks like. And from the previous one, if we were going to do that, that would be C5H12. And so a simple pentane will look like this. So we string our 5 carbons together, and then we surround it with our hydrogens. If you were to go on and take organic chemistry, you would get very fast at drawing these and how to name them. Now let's take a look. It's still a pentane right here. It's still C5H12, but it's a branched molecule. And so see how you have this 2-methyl butane? So what that means is that you start with butane. 1, 2, 3, 4 here. Okay, 4 of these. And the 2 means here that you're going to put a methyl group on carbon number 2. So on carbon number 2, we'll put a methyl group here like this. And then I'm going to go through and put hydrogens in all of the other places. So the methyl group, which is a CH3 unit, goes where one of those hydrogens will go. Okay. And for our last potential isomer, we have it's still C5H12, so it is still a pentane, but this is a little bit different. So it's 2,2-dimethyl. So that means that you put di means 2, so you put 2 methyl units on carbon number 2, and it's propane. So propane has 1, 2, 3 carbons, and then you've put a methyl group on each side of number 2. So then if you were to draw this one, it would look like this. It would look like a propane. Okay. And you would have 2 methyl groups on the middle carbon. And then you would have hydrogens on the outside carbons. Just like that. And these are just ball and stick models versus Lewis structures. So that's the difference between a straight chain and what we call branched chains. Okay, so these here are they are branched rather than straight chains, and we'll be coming back to that in a bit. Okay, now let's take a look at the combustion of octane. Okay, so remember, combustion always means burning with oxygen. And let's take a look at what this could be. So first of all, we have complete and incomplete combustion. So you can have a complete combustion that forms a CO2 and an incomplete or carbon dioxide and an incomplete combustion that only makes carbon monoxide. And what have complete or incomplete is going to be dependent on your ratio of fuel to oxygen. So here we have 2 to 25 versus 2 to 17. Okay. And then your engine temperature and your engine tuning is also going to depend whether or not you get CO2 and H2O or carbon monoxide and H2O. So let's kind of take a look at how these are balanced out. So first of all, we can go ahead and start here with our hydrogen. We have 18, we have 2 times 18 hydrogen. So because we have a 2 here, we'll put an 18 there. Okay. And then we have C8 here and a 2. Okay, so that gives us 16 carbons. So we'll put a 16 right here. And that means that we have 16 times 2. So from here, we have 32 oxygens. And from this one, we have 18 oxygens. And when we bring 18 plus 32 together, we'll get 50. And that is shown right here, 50 oxygens. So now we can take a look at that again down here. And here we have 17. Oh, actually, we don't want to do that one just yet. I always do my oxygen last because it's in two different places. Okay, so we have 2 and 18 for the hydrogens. So that'll still be 18 waters. Okay, and then we have the 2 and the 8. So we have 16 carbons. So we still have a 16 here, but now it's carbon monoxide. And we have 16 oxygens plus 18 oxygens, which gives us 34 oxygens, which is why here we have only 34 oxygens. So that's how that one would be balanced. Okay. All right, so now let's take a look at some of the basics of stoichiometry. Okay, and I think I forgot to mention it before, but we're up to slide 6 now. Okay, so stoichiometry is a term that's used to describe quantitative relationships in chemistry. And remember that quantitative means quantity. So we're going to always be looking at amounts or how much. That's always what that means. So basically, how much of a particular substance will be consumed, okay, so how much of our reactant, or formed, so that means products, in a chemical reaction. Okay. And a really, really big one here is always begin with a balanced chemical equation. We cannot do this correctly if we do not have one. Okay. And then we're going to be using a mole ratio, which we'll talk about in a minute, to go from the mass of one compound to the mass of another compound. So we need that way to link two different compounds together, and that'll be with something called a mole ratio. So here's an example of a reaction between methane right here. So we have 1 methane plus 2 oxygens yields 1 carbon dioxide and 2 waters. Okay, so let's take a look at what those mole ratios would be. Okay, and what we're going to be doing is we're going to be linking them to this balanced equation here. So you can see that you have this 1 in front of your CH4. So that means that we have 1 mole of CH4 and a 2 in front of the O2. So that means that we have 2 moles of O2. And this is one long ratio, and we have a 1 here, which brings us to 1 mole of carbon dioxide and 2 moles of water. Okay, so why that is important is that we can make mole ratios from this. Okay, so the mole ratios that we can make from this include the following. Okay, so we have 1 mole of CH4 to 2 moles, of oxygen. And then we can make the next one. So what we're doing is we're comparing these two here, like that. Okay. Now let's compare these two. This one, CH4 and CO2. So that means that we'll have 1 mole of CH4 to 1 mole of CO2. And now we're going to be looking at CH4 and H2O. Okay, and that means we'll have 1 mole of CH4 to 2 moles of water. Okay. So now we're going to look at oxygen and carbon dioxide. And a ratio can always be flipped over. So we don't need to make the ratios that would be opposite this. So now we say, okay, well, we have 2 moles of oxygen to 1 mole of CO2. Okay. And then we have, well, I'll look it up. I'll look here. We have the 2 moles of O2 and the 2 moles of H2O. So that would be 2 moles of O2 to 2 moles of H2O. We do usually write 2 to 2 instead of 1 to 1 in this situation. Okay. And then last but not least, we can only make one more mole ratio, and then we have made all the ones that are possible. And that's to look at carbon dioxide and water. And that would make 1 mole of CO2 to 2 moles of water. Okay. And you want to write all of these down in the space on your notes template. I will be asking for you to be able to find all possible mole ratios of a given equation. Okay, so make sure that you have all those. All right, here we are. And this is slide 8. Okay, so we're going to go ahead and practice this. So the first thing that we need to do, we're going to practice just as much of this as possible. Lots of balancing in case you're struggling with that still with chapter 3. So if I balance this reaction, I would start by saying, okay, I have C3 here. So I'm going to put a 3 in front of my carbon to give me 3 carbons. Okay. And then I would say, okay, let's see, what do we have for our next one here? We have is H8 and here we have H2. So let's put a 4 there for 4 waters. And this doesn't always work perfectly, but it's usually pretty close actually. Okay. And now what we're going to do is we're going to look at our oxygens. So here we have 3 times 2, or we have 6 oxygens here, and 4 times 0, or 4 times 1, so 4 oxygens here, which means that we need 10. So if we need 10 oxygen units here with our O2, then we need 5. And then I just usually put a 1 there, just so that I don't forget that. Okay, now let's take a look here. It says how many moles of water are produced when 6.20 moles of propane are burned in air? And then what mass of water is this going to be? Okay, so let's take this one step at a time. So first of all, we note that we have 6.20 moles of our propane here, and this is what we call our given or our known. And they're looking at how many moles of water. So that means that our water here is going to be our unknown. And that's what we're solving for. Okay, so our first question here, we'll call this part number 1, how many moles of water? Okay, and so what we're going to do is we're going to start with our given, which is 6.2 moles of our propane, C3H8. And now we can link this. We have 1 mole of propane to every 4 moles of water. So we can use that ratio here because we're at moles propane. So we would put down 1 mole of our propane here to 4 moles of our water here. Okay, and then the math for this is 6.2 times 4, and I can have 3 significant figures. So this becomes 24.8, and it's moles of H2O. And what I've done here is basically I've canceled moles and moles. So it's on the top. So top to bottom is how we cancel that. Okay, so now let's take a look at part 2 here. And part 2 asks for what mass of water is this? Okay, so hopefully you remember this from chapter 3, but we'll set up that 24.8 moles of water. And you're going to find how many grams this is by using your molar mass. So we put our 1 mole of water on the bottom so that those will cancel. And the molar mass of water, you could grab your periodic table and calculate that if you want the practice, is 18.015 grams of H2O. Okay, so when I do 24.8 times 18.015, then I get 447 grams of H2O, which is perfect. I need three significant figures, and I have three significant figures. Okay. So that's how we'll do that part. All right, so here we have our stoichiometry. And I always tell students, always start with a balanced equation. That is always and always very important. First of all, this is slide number 9. Okay, and this is a stoichiometry template. Okay, which means that this is what you're going to be following. And I tend to encourage students to put this template on your cheat sheet for the test, because it will help you remember what goes where. It's also printed on your notes template already. Okay, so now let's take a look at some stoichiometry practice. Okay, and this is, just checking to see, this is slide 10. Okay, and let's take a look at what some of these are. So first of all, we have the combustion of methane. Okay, so before I go any farther, I'm going to go ahead and write that down here. So the combustion of methane was an equation that we had before from slide 7. Okay, and that was that one CH4 plus 2 O2 yields 1 CO2 and 2 H2O. Okay, so always start with a balanced equation. And then it asks how many grams of oxygen. Oh, sorry. I need to be looking at the right place. There we go. How many grams of oxygen are required? So that means that grams of oxygen here is our unknown. All right. And then it tells us right here that we have 928 grams of CH4. So 928.0 grams, and this is our given. Okay. Is okay. And so there we go. Now, the next step here is to find your molar masses. Okay. So let's look at our molar masses, and we're going to put those in here. So the molar mass of CH4 is 16.043 grams per mole. And the molar mass of O2 is 31.998 grams per mole. Okay. And now we are ready to begin our stoichiometry. Okay, so remember that in stoichiometry, we start with our given, okay, and that is 928.0 grams of methane. And the next thing that we need is the molar mass of our given. And because we're starting here with grams, we need to put grams on the bottom so that it'll cancel. So this becomes 16.043 grams of methane per 1 mole methane. And it's always against 1 because it's a molar mass. It doesn't have anything to do with the values up here. The next piece that we'll need here is our mole ratio. And it's always unknown over known. So this becomes 2 moles of O2, and that's this 2 here from the balanced equation, per 1 mole of CH4. Right there. Okay. And the last piece that we have is the molar mass of our unknown. And that one is oxygen. So that one, that one, not a 2, a 3, 31.998 grams of O2 per mole O2. Okay. And when we calculate all of that through, we will get 3,702 grams of oxygen, and we have 4 significant figures that we were looking for. Sometimes you might also see this, it's asking for grams, so you definitely would leave it like this, but you might also see that as 3.702 kilograms of O2, because sometimes that's easier to do. Okay. All right. So you'll note that this process is not going to change, at least in this chapter, or probably not in this chapter, but this is just a standard stoichiometry. Right. And now we have another practice problem here, and this is slide number 11. And it says that how many grams of water, so here's our unknown, can be produced if sufficient hydrogen reacts with 26 grams of oxygen. So this is our given. And because it says sufficient hydrogen, that means that we have an excess of hydrogen and we can ignore that. So we always start with a balanced equation. So we have hydrogen gas. Hydrogen is a diatomic, so it needs to be H2. Okay. Oxygen is a diatomic, so it's O2. And we have our water. And we'll make some liquid water here. And we see that that O2 is there, so we'll need a 2 here for the oxygen, and 1 and 2 here for the hydrogen. Okay, so now we have our balanced equation. And we can start putting in a few pieces of information here. We're looking for grams of water. So this is our unknown. Okay. And the molar mass of our unknown is 18.015 grams per mole. We have an excess of hydrogen, so we're ignoring it. We have 26.0 grams of oxygen, and that's our given. And the molar mass of our given is 31.998 grams per mole. Now my setup is complete and I can begin my stoichiometry. Okay, so again, I start with my given, which is 26.0 grams of oxygen. The next thing is the molar mass of my oxygen. So I'm not writing in that template, but you should be able to see the template is exactly the same. The molar mass of my oxygen goes next, and I have 31.998. And of course, that has to go on the bottom so that we can cancel with grams O2 over here. Next, we need a mole ratio. So that's where that's one comes into play. So we have 1 mole of O2 here and 2 moles of H2O here. And the next thing is that we need a molar mass of our water. And that goes on the bottom so we can cancel out moles. And then we'll put the 18.015 grams of water on the top. And when we calculate this through, again, practice calculating it through, you multiply everything on the top, divide by everything on the bottom. Then for our answer here, we will get 29.3 grams of water. Excellent. All right, we are back now. We're up to slide 12 now. And let's take a look at some more stoichiometry practice. We're going to practice it over and over and over again until you're comfortable with it. Again, so in this case, we have 153 grams of S8. So we'll put that here. And that is going to be our given. We have excess P4, so we can ignore it. Okay, and it says what mass of P4S3? So we're going to put that right here. And we'll know that that is our unknown. Okay, now I'm going to start by balancing out my equation here. And so I noticed that I have P4 and P4. Okay, so I'm not going to do that first. I have 8 here and 3 here. So the only way to make those balance is with 24, because 3 times 8 is 24. And that's the lowest possible one that we can come to. So we'll put a 3 here. And we'll put an 8 here. Okay, and now we have 24 sulfurs. And if we have 8 P4 here in our product, then we would need 8 P4 here in our reactants. Okay, so now let's go ahead and finish our setup. And the molar mass for S8 is 8 sulfurs. Okay, so hopefully you are practicing that, and that is 256.48 grams per mole. Okay, and P4S3, 4 phosphoruses and 3 sulfurs. That will give us 220.076 grams per mole. And now I have completed my setup, okay, and I can begin my work. Okay, so I begin here with my given, again, which is 153 grams of S8. And the next thing, as we've been doing on the last few practice problems, is our molar mass. So we put in that molar mass, 256.48 grams of S8 in 1 mole of S8. And the next thing that we need is our mole ratio. So that's 3 moles of S8 here on the bottom, and 8 moles of P4S3 on the top. Okay. And now our last part is the molar mass of our unknown. So 1 mole of P4S3 contains 220.076 grams of our P4S3. Okay. All right. And when we calculate that, so that would be 153 times 8 times 220.076 divided by 256.48, and then divided by 3 Okay. And if you work through that correctly, you'll get 350. That little decimal point goes there because we can have 3 sig figs grams of P4S3 for your final answer. Okay. So that is our standard stoichiometry. All right. And we are up to limiting reactants. I'm going to, I think, go through limiting reactants, and then we'll take a break before we do yield. All right. So limiting reactants begins us with slide 13. Okay. So in the past, so I would note, well, we have a certain amount of one reactant and the other one is in excess. Okay. So the limiting reactant is the reactant that is completely consumed in a chemical reaction. And the excess reactant is the reactant that is left over after a reaction. So let's take a look at this. So when we look at our stuff here, you can see that we only need 2 H2 for every 1 O2. Okay, so in this, that means that the oxygen are the bigger red ones and the hydrogen are the little small ones here. And so here we have 2 H2 for 1 O2. All right, and here we have 2 H2 for 1 O2. And here we have 2 H2 for 1 O2. And when we do that, this top one, here you have 2 waters. And then here you have 2 waters in the middle. And here you have 2 waters here. And what you can see is that you have 1, 2, 3 oxygens here and here. So what that means is that 3 oxygens are left over because 6 hydrogens can produce 6 waters. 6 oxygens can produce 12 waters. That means that we can make only 6 waters. This becomes our maximum amount of product. Okay. And the one that is used first is our H2. Our hydrogen is our limiting reactant because it gets used up. Right. So there are a variety of ways of doing stoichiometry for limiting reactants. This is one method. There are other methods that you can use as well. I found that this is the easiest one to teach for students. So this is the one that I teach. But if you already know another method, or if you find another method online, I always say as long as your method gets you the right answer, then it is a good method. All right, so here we are on slide 15. Okay, and let's take a look at our balanced equation here. This is the same one that we had in the before. And so we already know that we have 3 and 8 and 8 for our balance there. Okay. So now it tells us that we're using 28.2 grams of P4. Okay, right here. And so, we know from looking at it that our molar mass of P4 is 123.896. And again, that's for phosphoruses from the periodic table. Okay. And now next we have 18.3 grams of S8. And the molar mass for S8, we actually found that one in the previous slide, is 256.48 grams per mole. And we want to know how much of our tetraphosphorus trisulfide that we can make. Okay, so this is our unknown. And the molar mass for this one is 220.076 grams per mole. All right, so my setup is complete, and now I can work through this. And again, there are different ways of doing this, but let's go ahead and learn this first way. And the first method is basically to just do stoichiometry with each reactant. That actually tends to take less time than finding your number of moles and then comparing the ratio, which introduces a kind of a different level of that. So let's go ahead and start here with the P4 that we've mentioned up here at the top. Okay. And if I do my stoichiometry with my P4, then I have 28.2 grams of P4. And next I need that molar mass of P4, 123.896 grams of P4 per mole. And next we need a mole ratio, and it's 8 moles of P4. And we are still going to our unknown here. So we would put 8 moles of P4S3 on the top. We're just ignoring the S8 completely. All right. And now the last piece here is the molar mass of our P4S3. Okay. And as I do that, 28.2 times 8 times 220.076 divided by 123.896 divided by 8, I will get 50.1 grams of P4S3. And this is the possible amount. So this is what's possible with the P4. Okay, so now let's take a look at what's possible with our S8. All right, so what's possible with our S8? Now we start with the given quantity that we started with here with our S8, which is 18.3 grams. And then we need the molar mass of our S8, 256.48 grams S8 per mole. And now we need a mole ratio, and that's 3 moles of S8 to 8 moles of P4S3. And we need, now this last piece is exactly the same because it's always going to be the molar mass of our unknown. And the molar mass of our P4S3, our unknown here, is 220.076 grams of P4S3. And 18.3 times 8 times 220.076 divided by 256.48 divided by 3 gives us 41.9 grams of P4S3. So you will notice now that this is our smaller quantity. So because this one is our smaller, this one is our answer. You have to identify on a test or on your homework which one is the answer. If you do not identify it, you will not get it correct, okay? This is the maximum amount that can be made. Another way of putting this maximum amount is this is what we would call our theoretical yield, just to give you a little bit of a heads up for what's coming next. And what that means is that S8 is our limiting reactant. And a lot of times I will ask you to identify that as well. Okay. Oh, I'm sorry. I said this was 15, but this is not 15. This one is slide 14. Okay. Sorry about any confusion there. Okay. Let's do another practice problem. All right, this one is slide 15. Sorry about that. Okay. And here we have, it's an already balanced equation. And since we're not listing anything, we have 1, 1, and 1. So this one's already balanced. And we want to know what the maximum mass or the theoretical yield of our final quantity here can be with 45 grams of methanol and 45 kilograms of methanol and 70 kilograms of isobutane. Okay, so this one is our unknown. And another way of writing, actually, never mind. I was going to say something, but I won't. So if you count up all the carbons and hydrogens and that one little oxygen here, you will get a value that is 88.15 grams per mole for your unknown. Okay, now let's take a look at what's next. Now, what is next is that these are both in kilograms, and you're going to need to convert that. Okay, so if you have 45 kilograms of your methanol, this is methanol here. Okay, remember that every kilogram has 1,000 grams in it. Okay, so what that means is that our known for this one is 45,000 grams of our methanol. And then let's look over here at our isobutane. And if we have 70 kilograms of our isobutane, and we need to convert from kilograms to grams, okay, then that will give us 70,000 grams of our isobutane. Okay, so next let's take a look at our molar masses. So our CH3 2CCH2, which is isobutane, is 56.108 grams per mole. Okay, and my CH3OH is 32.042 grams per mole. All right. Excellent. Okay, so let's go ahead and take a look at how to work this. So again, we're just going to be working our stoichiometry twice. So we're going to start out by working with this CH3OH. So CH3OH, which is our methanol, and we'll do that one first. And this tells us that we have 45,000 grams of methanol. And the molar mass for that on the bottom here is 32.042 grams of methanol per mole. Okay. And then we need our mole ratio. And in this case, it's 1:1. So 1 mole CH3OH to 1 mole of our MTBE. Holy cow, that's a mouthful. CH3 COCH3. Ooh, okay. And every mole of CH3COCH3 has 88.15 grams. And when we calculate that through, 45,000 times 88.15 divided by 32.042, we will get, we can only have three significant figures, so this becomes 124,000 grams or 124 kilograms of our final answer. Okay, now let's take a look um, at our isobutane. So this is for our CH3 2CCH2 or isobutane. Oops. And we begin with the given for that, which is 70,000 grams. And then the molar mass, 56.108 grams of our isobutane. Okay, per mole. It's hard to write. Okay, so we've got 1 mole again of our, now we have our mole ratio. So on the bottom, we have 1 mole of our isobutane. Okay. And on the top, we'll have 1 mole. This is the same as what we had before of our MTBE, CH33COCH3. Okay. And now this part in a limiting reactant is always the same. We have 88.15 grams. I'm not going to write this twice. And on the bottom here, we have the 1 mole CH33COCH3. And I'm just going to put an arrow up there so that I don't write that one again as well. Okay. So when I bring this one will give me 110,000 grams or 110 kilograms. So because this one is smaller, this is my answer for the theoretical yield or maximum mass that can be produced, which means that isobutane is my limiting reactant. Okay. All right, let's kind of take a look at where we're at. I think that is a really great place to stop. So I'm going to take a break here and we'll come back with slide 16.